Hello dear children, we have completed chapter number 13, Magnetic Effect of Electric Current, and started revising the chapter through the textbook. In the previous video lesson, we revised up till the solenoid and the magnetic field around the solenoid. Here is the next topic of the chapter, and that is the force on a current carrying conductor in a magnetic field. Under this topic, we have learned that suppose if we take a conductor, an aluminium rod is taken here, and that aluminium rod is connected with the help of connecting wire to the battery. And if we place this aluminium rod in a strong magnetic field which is produced by this horseshoe magnet, then we will observe that this aluminium rod will experience a force. So this is based on the concept that a current carrying conductor, when placed in a strong magnetic field, it experiences a force. We have seen an activity wherein we observed that the force experienced by the conductor depends upon the direction of flow of electric current. So observe both the figures carefully. See the polarity of the battery in the first figure and the polarity of the battery in the other figure. In both the figures, the polarity is exactly opposite, and therefore the force experienced by the conductor in every case is also different. So the force experienced by the conductor depends upon the direction in which the current is flowing through the conductor. After this, we also studied another activity wherein we observed that if we change the direction of magnetic field, look at the first and the second figure. In the first figure, North Pole is at the bottom, whereas in the second figure, North Pole is at the top. So the direction of magnetic field we have changed, and we observe that if we change the direction of magnetic field, the direction of the force experienced by the conductor also changes. So from both the activities, we can conclude that the force experienced by the conductor depends upon the direction of flow of electric current and also the direction of magnetic field. Alright? Then the direction in which the force is experienced by the conductor is given by Fleming's left-hand rule. And it states that if you stretch the three fingers of your left hand, that is the thumb, the index finger and the middle finger, in such a manner that they are mutually perpendicular to each other, then if the index finger is in the direction of magnetic field and the middle finger is in the direction of the current, then the thumb always represent the direction in which the force is experienced by the conductor. And with the help of this diagram, you can very well understand this. After this, there is an application of this magnetic field in the field of medicine also. We all are aware that our body is good conductor of electricity. There are so many ions present inside our body. So when we touch something, our nerves carry an electric impulse to the muscles we need to use. This impulse, they produce a temporary magnetic field. Such fields are weak field. The two main organs in our human body where the magnetic field produced is significant. These two organs are heart and brain. The magnetic field inside the body forms the basis of obtaining the images of different body parts. And MRI, that is magnetic resonance imaging, this is a technique which is used to see the image of different parts of the body. And this is how the magnetic field is useful in case of the medicine. Alright, after this we studied about electric motor, and it works on the principle that when a current carrying conductor is placed in a strong magnetic field, it experiences a force. We saw different parts of electric motor, and we also studied about the working of electric motor. In the construction of electric motor, we understood that a rectangular coil, which is also called as an armature, it is placed between the magnetic field, and this magnetic field is produced by two horseshoe magnets. One acts as a north pole and the other acts as a south pole. The two free ends of the rectangular coil is then attached to two split rings, which are also called as commutator, and on the commutator two carbon brushes are pressed. These two carbon brushes are then connected with the remaining part of the circuit with the help of connecting wires, which are then attached to the battery and the plug key. The commutator, they pressed against the carbon brushes, they are not attached with the carbon brushes. Carbon being good conductor of electricity, so when the electric current is passed through the circuit, it first goes through the carbon brushes and then through the commutator it is going through the armature coil. So through this diagram you can just see that the moment we switch the current on, the armature coil starts rotating in the strong magnetic field. And how it rotates, in which direction it rotates, that can be given by Fleming's left-hand rule. After this topic, children, we studied about electromagnetic induction. This electromagnetic induction is defined as inducing an electric current into the coil by changing the magnetic field. So we saw this activity wherein we observed that when the magnet is stationary, when we are not changing the magnetic field, the reading in the galvanometer is 0. Galvanometer is a device which is used to sense the current in the circuit. So here we are observing whether current is flowing through this conducting wire or not. So when the magnet is stationary, there is no current which is flowing through the conductor. But the moment we take this magnet in and out of this coil, we observe that the reading in the galvanometer changes. That shows that when we change the magnetic field, current is induced in the coil, and this current is called as induced current. There is one more method for inducing the current into the coil. Let us observe that. In this method, we have taken the coil of the wires and both the coils are placed adjacent to each other. One coil is connected to the battery and the other coil is connected to the galvanometer. When we switch the current on through the first coil, we can see the change in the deflection of the galvanometer in the other coil. That shows that the moment we switch on the current, again we switch off the current. Every time we do this, there is deflection in the galvanometer. That shows that change in magnetic field induces current into the coil. And in this case, how are we changing the magnetic field? Because we are already aware that when we pass current through the conductor, it produces magnetic field around it. And we are continuously putting the plug key on and off, and that is how we are changing the magnetic field. You can just observe this with this diagram. The moment we pass current through the first coil, it produces magnetic field around it, and in the second coil, current is induced due to that. So you can see the flash of light in the second coil. Alright children, so this was about the electromagnetic induction. And the induced current into the conductor can be given by right hand thumb rule. And right hand thumb rule states that when you stretch the three fingers of your right hand, the thumb, the index finger and the middle finger in such a manner that they are mutually perpendicular to each other, then suppose if the thumb is in the direction of the motion of the conductor and the index finger is in the direction of magnetic field, then the middle finger will always give us the direction of induced current. Alright children, so with this is the next part of the lesson, and this part is being deleted for this particular year from your syllabus. So we do not have electric generator, we do not have domestic electric circuit. Our chapter ends at electromagnetic induction. So it was an easy topic, I suppose, and you all must have understood it. Please revise the topic once again, go through all the videos and try to solve the questions which are given you in the form of an assignment. So see you all in the next video lesson. Until then, bye and take care.